Good day, Miss May. We are Bilupura and Tamang, and today we are going to present the material selection of a chemical reactor. The production of phenol is usually done through the Doe process. Alternatively, producing phenol through oxidation of cyclohexanone with oxygen at high temperatures is possible. This reaction is illustrated in the figure. The oxidation of cyclohexanone to produce phenol is a non-elementary reaction that follows an elementary rate law. Our paper aims to design a reactor system to oxidize cyclohexanone to produce phenol that will give cyclohexanone conversion of 89 to 92 mole%. All the components in this reaction are in the gas phase at 200 to 250 degrees Celsius. Accordingly, the operating pressure is set to 0.8 bar to avoid the organic components diffusing from the reactors in case of a leak. The oxygen used in the reaction can either be available as a highly pure reactant or purified air. The feed, cyclohexanone, a byproduct in a separate process, will be used for this reaction system and produced around 4,500 to 5,000 moles per year at about 85 to 90 mole% in a gaseous form, with other components inert to oxygen at a temperature of 200 to 250 degrees Celsius. Moreover, at the temperature of 200 degrees Celsius, the specific reaction rate is equal to 1,500 liters per mole per hour, and the activation energy of the reaction is 110 kilojoules per mole. The reactor chosen for the reaction is a plug flow reactor. Accordingly, the appropriate material selection is a significant factor in developing a product that will operate under specific conditions. Ideally, this product must satisfy all design requirements defined. Because there is a wide range of materials available for various production processes, during the selection process becomes a tedious task. Missing a possible attractive alternative is a possibility. However, this possibility is toned down by following a systematic selection procedure. The selection process is grouped into 4 steps. 1. Analysis of the performance requirements. 2. Initial screening of the materials. 3. Using quantitative methods in material selection. And 4. Selecting the optimal material for the equipment. Through Ashby's plots, the probable materials to make the reactor will be narrowed down to a few ones. These materials will be further narrowed down during the matrix selection. Since service temperature is critical in the reactor's design, the service temperature against Ashby's ultimate tensile strength plot is utilized. So for the quantitative method in material selection, the performance index is used to weigh the different materials, while the digital logic method will be used to assess the material selection process further. The function of the PFR is to hold the components for the oxidation reaction, given that the temperature is in the range of 200 to 250 degrees Celsius at the pressure of 0.8 bar. Primarily, the objective is to choose a material that maximizes strength without failure at a modest cost. Now, all engineering materials must be considered to determine the candidate materials for the construction of the PFR. The 5 categories are 1. Metals, 2. Polymers, 3. Elastomers, 4. Ceramics, and 5. Hybrids. Since the reaction must be operated at a high temperature, the material must withstand extremely harsh temperature conditions and must have considerable yield strength that is higher than 100 megapascal. The number of materials can be narrowed down using Ashby's maximum service temperature chart, as shown in this figure. So the materials under the blue shaded region are the desired materials that are included in the following selection. Based on the Ashby plot, the materials that are appropriate to use in designing the reactor are carbon fiber reinforced polymers, carbon steels, cast irons, low alloy steels, titanium alloys, nickel alloys, stainless steels, tungsten alloys, silicon nitride, aluminum oxide, silicon carbide, boron carbide, aluminum nitride, silica glass, glass fiber reinforced plastics, polyether ether ketone, magnesium alloys, and aluminum alloys. Since hot phenol can attack aluminum, lead, or lead, magnesium, and zinc, these materials are already excluded from the selection process.
So from the figure, the possible material to be used is further narrowed down to CFRP, carbon steels, low alloy steels, titanium steels, nickel alloy, stainless steels, tungsten alloys, silicon nitride, aluminum oxide, silicon carbide, glass fiber reinforced polymer, and polyether ether ketone. Since silicon nitride and aluminum oxide and silicon carbide are not suitable materials for the reactors because these are ceramics and glass fiber reinforced polymer and PEEK are polymers, these materials are excluded from the selection. For ceramics, their resistance to fracture under load-bearing application is significantly lower than that for metal alloys. Also, ceramics have low stress tolerance and high brittleness, making them undesirable for the reaction. To further narrow the materials into four, their performance index are compared. So the table shown in the slide shows their performance index. The performance index is calculated using the equation P is equals to um, the Young modulus to the power of 1/2 over the density. So shown in the table, we can see that carbon steels, low alloy steels, and stainless steels actually has one of the highest performance index. So table 2 shows the comparison of material properties using digital logic. So in selecting the material to construct the PFR, several factors need to be considered. These properties include tensile and yield strength, stiffness, hardness, corrosion resistance, thermal conductivity, and cost. The digital logic method is used to assess the properties mentioned to narrow down the selection. The digital logic method is used to compare the properties from one another. The number of positive decisions is then listed and scaled to obtain weight fractions resulting in a sum of 1 for each property. Physical, chemical, and mechanical properties have different numerical values and units, which could result in properties with higher numerical values having a significant effect than its weighing factor warrants. Accordingly, a scaling factor can be introduced such that more critical properties are given priority over the others. The value of the properties are scaled such that the best property in the list is given a rate of 100. Although this is not always the case, as some properties are better off having a smaller rating than others. This scaling factor will convert the properties to a dimensionless value. So properties such as corrosion resistance do not give a concrete value. Instead, descriptive ratings such as excellent, good, and fair. In this type of ratings, a numerical value to how good or bad the rating um, is used. For example, a rating of good can be given a relative scale of 3 while 1 is poor. Further, the table shows how the properties evaluated using the scaled factor. 1 and 0 in this case pertains to the relative importance of the property, where 1 is important while 0 is less important. Among the properties listed are corrosion resistance, which has the greatest value for relative emphasis coefficient, followed by tensile strength, thermal conductivity, cost, hardness, and stiffness. It should be noted, however, that this type of evaluation is not meant to replace the designer's own intuition, but rather help them decide easier which material is best suited for the task. So table 3 shows the technical data of the materials chosen or narrowed down. So while table 4 shows the performance index of said materials, which shows that stainless steel actually has the highest performance index, which means that this is the material that should be used in the design for the PFR. So table 5 shows the technical data of the stainless steel materials. So we know that there are a lot of stainless steel. So in this case, the best suited stainless steel material is 304L, 304, 316, and 316L. So um, table 6 shows the performance index of said stainless steel materials. In this case, it shows that 316L has the highest performance index, which means that it is the best suited material for the construction of the plug flow reactor. Um, so the appropriate material to use for the construction of PFR for the 89 to 92% conversion of cyclohexanone to phenol is 316L stainless steel. So that's all, and thank you, Miss.